Just when scientists thought they had uncovered all the universe's surprises, the James Webb Telescope revealed something truly unexpected: gigantic, fluffy exoplanets that resemble cosmic cotton candy. While their nickname might sound whimsical, these planets present a serious scientific puzzle. Their incredibly low density makes them appear far too light for their massive size, defying our current understanding of planetary formation. In theory, the formation of gas giants like Jupiter follows a clear process. They begin as solid cores with at least 10 times the mass of Earth, accumulating their thick gas envelopes early in their system's development. The gravitational pull of the growing planet ensures it retains its atmosphere, even against the powerful stellar winds of its host star. At least that's how it's supposed to work. But these newly discovered exoplanets challenge that framework entirely, forcing scientists to rethink what they thought they knew about how planets take shape. That's the theory, at least. But when we look at real discoveries in space, we find exoplanets that completely defy expectations, challenging our current models of planetary formation. One of the most puzzling cases appeared on the star charts in 2017. Around 212 light-years from Earth lies WASP 107b, a gas giant unlike any other. This alien world completes an orbit around its star in less than 6 days. Initial observations suggested it was similar in size to Jupiter, but deeper analysis over the following years revealed something astonishing. Scientists used the radial velocity method, tracking the minute wobbles of its host star caused by the planet's gravitational pull, to calculate WASP 107b's mass. The results were shocking. Despite being as large as Jupiter, this exoplanet weighs only about 30 Earth masses, meaning it has just 10% of Jupiter's mass. This discovery raises a massive question. How can a planet so big be so light? It's a cosmic mystery that's forcing astronomers to rethink everything they know about gas giant formation. Based on these findings, scientists ran model calculations and determined that WASP 107b's solid core could be no more than 4 Earth masses. This means the planet is extraordinarily fluffy, with an incredibly low density resembling cotton candy. But that raises an even bigger mystery: how did such a low-density planet even form? And more importantly, how has it managed to hold on to its massive gas envelope without losing it to space? This question becomes even more perplexing when considering WASP 107b's close proximity to its star. Being so near, intense stellar radiation should have stripped away much of its atmosphere. Yet somehow, this cosmic anomaly has defied expectations. Astronomers quickly realized that this cotton candy planet was an extreme outlier, an object that completely breaks the conventional understanding of how planetary mass and size relate. But if researchers had already been aware of the Kepler-51 system, they would have realized that these so-called absolute outsiders aren't as rare as they once thought. Located 2,600 light-years away in the constellation Cygnus, Kepler-51 is a sun-like star that hosts not one, not two, but 3 of these strangely low-density planets. Faced with an even bigger cosmic puzzle, a team of researchers led by Jessica Libby Roberts of Pennsylvania State University decided to take a closer look. Using the powerful James Webb Telescope, they set out to unravel the mystery of how these bizarre, fluffy worlds could exist and what they might reveal about planetary formation in the universe. But when scientists aimed the James Webb Telescope at Kepler-51 before the expected transit, they were caught off guard by an unexpected twist. The planet's shadow appeared far earlier than predicted. Instead of witnessing the start of the transit, they had unknowingly tuned in just in time to see its conclusion. The numbers told a shocking story. Kepler-51d had begun its journey across the star a full 2 hours ahead of schedule. Normally, minor deviations in transit timing, just a few minutes, can be explained by gravitational influences or orbital shifts. But a discrepancy of this magnitude was something entirely different. So what could have caused this planetary misalignment? That was the million-dollar question. Co-first author Kento Masuda from the University of Osaka admitted that the early arrival of Kepler 51d left him and his team completely baffled. No matter how they adjusted their models of the three-planet system, nothing could account for such a drastic shift. One thing was certain: this wasn't a mistake by the James Webb Telescope. The data was solid. Something strange was going on in the Kepler 51 system, and unraveling this mystery could mean rethinking what we know about planetary orbits and interactions. The mystery deepened when the early transit wasn't just a one-time anomaly. It was confirmed by the Hubble Space Telescope and multiple Earth-based observatories. The evidence was undeniable. But what could possibly explain this cosmic curveball? The answer lay in an expanded model of the system, one that included a fourth, previously unknown planet. This elusive world, now dubbed Kepler 51e, likely orbits farther out on a more inclined trajectory. Because of this tilt, it never transits directly in front of its star from our viewpoint on Earth, but its gravitational influence is enough to disrupt the motion of its neighboring planets. Further analysis suggested that Kepler 51e is another gas giant, similar in mass to its three siblings. This means the Kepler 51 system isn't just home to three bafflingly lightweight, candy floss-like planets. It's actually a quartet of cosmic oddities. Even with this new addition, though, the planets are still far too fluffy to fit into our conventional models of planet formation. Adding to the intrigue, most of these cotton candy worlds tend to be solitary within their systems. Yet here, we have four in one place. Could there be even more hidden planets beyond Kepler 51e? Scientists are now eagerly turning to the James Webb Telescope's high-resolution spectrograph, hoping to peel back more layers of this planetary enigma and finally uncover what makes these puffed-up worlds so unique. The Kepler 51 system isn't the only planetary arrangement leaving scientists scratching their heads. While its cotton candy planets challenge density expectations, another system, WASP 132, is turning planetary formation theories upside down with its unexpected diversity. Located about 400 light-years away, WASP 132 boasts a lineup that looks like a cosmic mashup: a super-Earth, a hot Jupiter, and a massive ice giant, all orbiting the same star. This combination is unusual because hot Jupiters, gas giants that orbit extremely close to their stars, are typically lone wanderers. Their formation models suggest they should have formed farther out in their systems and only later migrated inward, bulldozing any smaller planets along the way. Yet here, a hot Jupiter coexists with two very different planetary types. How did this happen? Did this gas giant move inward without disrupting its neighbors? Or did these planets form under conditions that defy our current understanding? These questions push astronomers to rethink planetary evolution. WASP 132 proves that nature doesn't always follow the rules we expect, reminding us that the universe still holds plenty of surprises. The WASP 132 system continues to baffle scientists with its unexpected planetary lineup. The super-Earth orbits even closer to the star than the hot Jupiter, completing a full lap in just over a day, while the gas giant takes about 7 days. But the true outlier is the ice giant, lingering much farther out, with an orbit stretching over 1,800 days. Adding to the intrigue, the star's light curve hints at another hidden companion, possibly a brown dwarf. These mysterious objects sit between planets and stars, blurring the line between the two. However, the presence of a hot Jupiter in this system challenges existing migration theories. Normally, such gas giants form farther out and drift inward, disrupting smaller planets in the process. Yet here, the super-Earth remains intact, and the ice giant's orbit appears undisturbed. This suggests the hot Jupiter's migration was unusually smooth, avoiding the chaotic gravitational interactions expected in such a system. But exactly how this happened remains a mystery. If you're enjoying these cosmic puzzles, don't forget to hit that subscribe button and give this video a thumbs up. There's always more space to explore, and you won't want to miss what's next.